Hello, everyone, and thanks for tuning in to this talk about electromagnetic simulation of PCBs using COMSOL Multiphysics. My name is Nathaniel Davies. I work as an application engineer for COMSOL in the UK at our Cambridge office. So I do things like the technical support, training courses and things like that. My specialism is in the electromagnetic modules of COMSOL. Which hopefully you'll know what I mean by that by the end of this talk. So before I start talking about software, I thought I'd just give a mention of why we might be interested in doing modeling or simulation of printed circuit boards, or PCBs, as I'll refer to them for the rest of this talk. So PCBs are very common devices in just about any kind of electronic product these days. And the first thing we might be interested in doing with our PCB, whatever its purpose is, might be in quantifying the device performance, as I've said on the left of this slide here. So this is essentially working out or making sure that the device works in the way that we intend it to. So this might be looking at things like the coupling efficiency between different parts, signals on different parts of the PCB, maybe inductances of tracks on the PCB, or S parameters or resonances if you're thinking more in the RF regime. The second and equally important thing we might want to do is to minimize any unintended behavior. So for example, I might have crosstalk between different lines on my PCB, which is unintended, and I want to get rid of that or minimize it. I might have some kind of parasitic inductance between different parts of the PCB, or I might have more sort of multi-physics effects, like I might get some heating or some thermal deformation causing mechanical stress, which I want to minimize or avoid. And we could simulate all of these things for that purpose. The final thing we might want to do is look at the interaction with the environment. So this is sometimes referred to as EMC or EMI. So this might be looking at, is my PCB emitting electromagnetic radiation? And trying to keep that below some standard, perhaps, or equally, if the environment contains electromagnetic radiation, is my PCB immune to that radiation? So can it function despite that? And sort of similar to immunity is shielding, so designing some kind of shielding setup so that my PCB is shielded from the electromagnetic environment that it's in. So in all three of these categories, we can create a computational model using modern computational software such as COMSOL, which can do any of these things for us. And importantly, it allows us to do so without creating a lot of different prototypes and performing perhaps costly and time-consuming experiments to design our PCB with these goals in mind. So COMSOL Multiphysics is one such software which we can use to perform modeling of many different phenomena, including PCBs. So COMSOL Multiphysics has three parts to it. It has what we refer to as a model builder. This is in some sense the core, which allows us to model physical or chemical phenomena in a sort of joined up way. Once we've done that, we then also have what we refer to as an application builder, which can allow us as the modeling engineer to create an application which we can then distribute to other people who maybe don't know the ins and outs of COMSOL Multiphysics or indeed simulation in general, so that they can sort of check in with the model results. So I might make an app and send it to either a colleague or a customer who maybe wants to tweak the design a little bit and see what results that causes in the outputs, without needing themselves to be a modeling engineer. And then the final piece we have is called a model manager. This is more of a sort of version control or organizational tool, which allows us to coordinate using the different models and apps across a large organization between different users. So for the rest of this talk, I'm basically going to focus on the model builder side of that. So within COMSOL Multiphysics' model builder, essentially what we can do is we can build computational models of one or more different physical or in some cases chemical phenomena. So for example, as you can see on the slide, I might produce an electromagnetic model of my PCB. But this is where the real power of COMSOL Multiphysics, in my opinion, comes in. You can also then create models of the same device in other areas of physics. For example, I might make a thermal model of the cooling for my PCB. And then I can perform a full sort of two-way coupling between these models within one simulation package. So I can derive the heat sources from my electromagnetic radiation or currents, and then I can use them to model the maximum temperature that my PCB might come to. And I can also model the back coupling to take into account temperature dependence of, let's say, the resistivity of any metal components in my PCB. So essentially one big joined up software environment where we can model any of these wide areas of physics or chemistry and combine them in an arbitrary way. Sat on top of this, we also have some more general tools. So you can actually also define your own equations if you want to get a bit more custom about this, because under the hood, what COMSOL is actually doing is solving a set of differential equations, and we can modify them to suit. There are also optimization tools if you want to sort of work in reverse and try to design an optimal component for achieving some goals, such as minimizing the temperature rise, for example, within the software. And there are interfaces to various other useful software products from other companies, such as MATLAB and Simulink, as well as various CAD tools if you use those to derive your geometries. So for the rest of this talk, I'm going to focus in on the electromagnetic part of COMSOL, just to show you one example of the kinds of models that we can make. So within COMSOL, we can model the full electromagnetic frequency range. So starting from very low frequency effects, either stationary like DC currents or low frequency AC currents, up through the sort of RF range where we get radiative effects and radiation becoming important, and all the way up to optics and even ray-based optics on the scale of rooms or larger. And there are different tools within COMSOL to work in these different frequency regimes. So for today, I'm going to focus in on the lower frequency side of things in what we refer to as the AC/DC module, although you can rest assured that we have tools to model these higher frequency phenomena equally well if you're interested in that too. So for low frequency modeling of PCBs, there's a few different tools that COMSOL gives you. We refer to them as physics interfaces. So essentially, they set up different phenomena that you might want to solve for, or equivalent, you can think of them as making simplifications to the underlying equations of the physics that's being solved. So the core one that I'm going to show you today is called magnetic fields currents only. So this is for very fast and efficient computation of the magnetic fields due to currents being carried by conductors in a free space, which we approximate as a vacuum. So this can be tracks or coils on a PCB, for example, and you might want to compute the electromagnetic field, and then maybe you want to compute the different induced currents that go on. And this physics interface can do so very efficiently. There is also one called magnetic fields, which is a bit more complicated for things like permanent magnets and anisotropic materials and thin layers. There's one called magnetic and electric fields, which works a bit better at lower frequency for capacitive effects. And then there's a final almost add-on product called the electric circuits interface. So this allows us to create, either create within COMSOL or import a symbolic circuit of idealized objects like resistors, capacitors, inductors, and so on. So we can either create that within COMSOL, or we can import it from a SPICE netlist, for example. So the idea of this is that you can create these circuits and couple that circuit to a full 2D or 3D model of a component of interest. So for example, I might have some circuitry which is producing some exciting waveform, which I model as a SPICE circuit, and then I use that waveform to feed or to excite my 3D PCB model. So that's a sort of overview of what the software can do. As I said, just to give you one example of what of how this works, I'm now going to show you a live demonstration of how to use the magnetic fields currents only interface to quickly extract the cross inductance matrices and the electromagnetic fields around some example PCB coils. So these PCB coils will look as you can see on the slide, and designs like this are common in very wide range of consumer electronics. So we will go around and excite these coils at 200 kilohertz, which is just a test frequency I've chosen off the top of my head, and work out the inductance matrices between the different coils. So without further ado, if I can switch over and share my screen now, please. I can show you how to do this within COMSOL Multiphysics. So what you can see on the screen right now, hopefully, is a blank version of COMSOL Multiphysics as it is when we first open it up. So I can create just a blank computational model by clicking the blank model button and start from scratch, as it were. But there is also a model wizard, which will ask me some questions about my needs to pre-populate the COMSOL desktop. So let me just click on the model wizard. So we're going to be asked some questions. The first thing is, okay, this device that I'm interested in, what is the dimensionality? Hopefully this is fairly self-explanatory. Is it a 2D, maybe planar device? Is it a full 3D device? It is in this case. Or maybe does it have some kind of symmetry? So I have a 2D axisymmetric version, for example, for things that have cylindrical symmetry. So the thing I showed you on the slide was very obviously a 3D object. So we can click on the 3D button. Next, we're asked to select a physics. So this is COMSOL asking you to select the sort of type of physical phenomena you're solving for. And I have a big list of these because I have a fully unlocked version of the software. So you can see the great capabilities of this. There's options not just to do electromagnetic modeling, but also even chemical modeling, electrochemistry, fluid flow, plasma modeling, and so on. So in this case, I'm looking at low frequency electromagnetism, where low frequency means that I can neglect radiation. So the wavelength of any radiation associated with any changes in electromagnetic fields in my device is very much larger than the device itself. And in this case, I can use the AC/DC branch, and I have a big list of different what we call physics interfaces that can solve in here. So in this case, I want a full electromagnetic field. That's this section here. So I don't want to make any simplifications in that sense. And you can see the options, or some of the options I mentioned on the slide appearing here. So you can click on the one you want. In this case, I will go for magnetic fields currents only, because I want to solve for the full magnetic field. And I have some currents, but I don't have any permanent magnets. So once you found the one you want, you press the add button, and then you go through next to the study by pressing this next button down here. You're then asked to select a study. So if the physics interface, the previous one was asking the type of phenomena we're solving, the study is defining how we're solving. And in this case, there's essentially only two options. Are we solving stationary, which means that would be DC currents, no time changes at all, or are we solving frequency domain, so at a known frequency? And we have these frequency domain source sweep with initialization and stationary source sweep with initialization, which are tailored study steps for this purpose. And I'll talk about what this last part means later on in the modeling process. But for now, we know we're solving at a fixed frequency, as I said, so I can click the frequency domain version and then press this done button down. And we now go through to the COMSOL desktop, which you'll now see for the rest of the modeling process. And it's been pre-populated according to the options that I just selected. So this desktop is made of a series of panes. So let me just mention what they are quickly. On the left here, we have the model builder pane, first of all. So this is in some sense the heart of a COMSOL model. It contains an overview of everything that is in the model at the current time. And it has a sort of order to it, from defining any inputs to the model, like input parameters, through building a geometry, setting up your materials and your physics, through to solving the model, and then finally looking at any results and post-processing you might want to do. Within this model builder tree, we have a series of what's called nodes. And when I click on these nodes, there are settings which appear in this settings pane here, which I can change using the various drop-down boxes and tick boxes and so on. There's also a graphics pane over here, which will give relevant graphical information as we go along, like 2D and 3D rendering of the geometry, which we can use to sort of point and click on. At the bottom here, we have some text-based windows for like error messages, progress messages, that sort of thing. And then at the top here, we have a ribbon bar split into sections. So the ribbon bar gives a quick and easy overview of everything that you can add to the model. So there's actually two ways of adding things to the model builder tree. You can either click buttons in this ribbon bar, or you can right-click on the model builder tree. They do the same thing, it's just personal preference. I prefer the right-click method personally. So the idea of building this COMSOL model is going to be to work from top to bottom of this model builder, adding nodes, either by right-clicking or using the top bar, then setting the settings of those nodes using the settings pane and the graphics pane, if relevant, until we've got all the way to the bottom and we can see the results that we want. Okay, first of all, these top sections that I'm highlighting here, these are inputs to the model, like parameters and things like that. So these are optional. And since this is a simple demo, I will skip over these because they are only optional. The first thing that we do always have to do is find in some way a geometry. So if I go to the geometry section, I can either go to geometry up here, or I can right click on this geometry one node. They do the same thing. You can see the different things I can add to my geometry. Now there's two ways of building a geometry in COMSOL. The first is to just do it. You know, I can click block here and it will add a block, and I can build up my geometry that way within COMSOL. The second way is to import it. So to save time, I'm going to import a geometry in this case. Although importantly, I'm importing a pre-made geometry from within COMSOL, but equally you could be importing a CAD file here. And COMSOL can import most common commercial CAD software files, so things like SolidWorks, AutoCAD, and all that sort of thing. We can import files from those softwares. So if I add this import node, then in the settings pane, I can click Browse. And then if I just go to my desktop and I can find this file here, so this is one I prepared earlier within COMSOL. You can think of this, that this could be your CAD file from your CAD software if you want to. So I can press the open button and then the import button here, and we should be able to see the geometry that was contained in that file, which is these PCB coils, similar to what I showed you on the slide. Now that I have a geometry, I can quickly mention how to manipulate this graphics pane. So if I left click and drag, you will see it rotates around in 3D, like so. If I right click and drag, it translates, like so. And if I hold the mouse scroll wheel and drag, it zooms in and out, like so. So very easy to sort of inspect your geometry. So these are my coils I want to model. I do need to make one other modification to this. So COMSOL is what's called a finite element solver. That's the numerical method it uses, if anyone knows of that. And therefore, we need to draw in an object in the geometry everywhere where we wish to take into account the electromagnetic field. Now, in the case of these coils, there would be a very significant magnetic field looping up in the air around these coils. So I need to add a block of air in the geometry in which I'm going to compute those magnetic fields. So the simplest way to do that is to just right click on the geometry node, and we have these same options we had before. And you can see I can just add basic shapes. So I can add a block. Once I've got this block, I can type into these boxes, how big is the block and where is it? So for example, I might say, and these are numbers that I prepared earlier, the block is 5 centimeters in width, and you'll notice this square brackets allows us to do a unit conversion automatically. It is 6 centimeters in depth, and it is 2 centimeters in height. And it is centered, if I go through this drop-down menu, at the origin. And these are numbers that I know that I prepared earlier, so that I know if I now go to the top here and press the Build All Objects button, this will first of all import the coil and then build this block. And this block has been designed to completely encompass the coils, so I can compute the electromagnetic fields everywhere around them. Now, I can't sort of see anything anymore. So it's probably useful if I just go up to the top here. So I've got a lot of buttons up here where I can control my graphical rendering. And in this case, I can press this wireframe rendering button to just switch over to wireframe mode. And now we can see inside and we can see the coils nicely tucked in there. Okay, so once we've got our geometry and made any modifications suitable for physics-based analysis, like adding this block, the next thing on the list is this materials section. If I click on it, we can, once again, if I right click, we can add various materials in various ways. So in this case, I would like to tell COMSOL that the block is made of air and that the coils are made of, let's say, copper. So there's two ways I can do this. I could either add a blank material, then I could just type in the material properties of copper or air myself, or I can click add from library, which is this top one, and then we get a library pop up over here of common materials that COMSOL already knows the properties of. So for example, if I go to this built-in section here, we can see various options, including air and copper. So if I just go to air and double click it, then we see air appears over here. And if I look in the settings pane, here are all the material properties of air that COMSOL knows from its library, some of which we might use, some of which we definitely won't in the context of an electromagnetic model. Okay, so that's air. Similarly, I'll just double click on copper, which we'll need for the coils, and then I'll press this cross button here to close this pane up. So I would like everything to be copper except the air block. So the way I can do that, you'll notice this copper here has a little warning saying selection is empty. So this selection is empty is telling me that I haven't put the copper anywhere. So I can change this just by pointing and clicking to assign something to be copper. So for example, if I hover over, the thing I'm hovering over goes red. If I click it, it goes blue. This thing gets assigned as being copper. If I don't like that, I hover over a blue thing, it goes green. I can click again, left click, and it gets removed. So very easy to sort of point and click to make these assignments. If I want to highlight something inside the geometry, I can click the mouse scroll wheel forward and it just highlights things under the flicks between the things under my mouse, like so. So I can point and click to make these assignments. I can also shortcut this a bit with the copper because I can press Control A to select everything and then just click on the air domain to deselect air. And now everything except the air block is assigned as being copper. That's very good. The air material, because it was the first one I added, has been added in all domains and then has been overridden in the copper domains. So that's perfectly fine in this case. The remainder gets left as air. So next up, we have the physics interface. So this sets up the field equations for the electromagnetic field. The good news is it does it for you, so you don't necessarily need to know what these equations are. They are basically Maxwell's equations. And you can actually have a peek in here to see what the equations are if you want to. But if you don't want to, you can just ignore that. So the overall parent node here tells us where we're solving these equations. Everywhere is fine, all domains. It has a default free space node. So this just enforces the relevant equations in the air domain. It has a default boundary condition called exterior boundaries. So COMSOL needs a mathematical constraint on the equations on the outside boundaries of this thing in order for the equations to be sort of properly constrained in the mathematical sense. So it gives us one that it will use if we don't override it. In this case, this is designed for the external boundaries of this domain so that it acts like the fields are allowed to sort of spread away to large distance and not be truncated in any way. So this is designed to be okay in this case. And finally, we have an initial values node. This is the starting guess that the solver will use for some iterative procedure. So you shouldn't need to change the inputs of this unless there's something going wrong. So the way to set this up then is we can once again right click and we can add various things. I've got a few options. So basically in this case, all I need to do is tell COMSOL that my coils or are conductors. You can probably see what I'm going to add here to do this. And then once I've done that, I'll also have to tell it where the feed points are for my coils because it doesn't necessarily know that based on the geometry. So I can just add this conductor option And then I can select anything in the model which is a conductor. So once again, perhaps I go Control A to select everything, and then I just deselect the air, and everything else is a conductor. Okay, so these are all conductors. They are disconnected conductors. You can see that quite obviously here. So they're not really all one conductor. In fact, there are 12 coils here. There's 4 here, and then 4 that cross over between the sides. So I can automatically detect that. If I go to my conductor and right click, we have this split by connectivity option. If I click this, COMSOL will detect which pieces are connected to one another. So you can see it's detected that I have 4 coils on this side, which is named 1, 2, 3, and 4 running along there. They were all connected loops. Then it has 4 that cross over in the middle. You can see that 1 there, 2, 3, and 4, and then 4 on the other side. So it's all done that automatically for us. The remaining thing then is we have to tell COMSOL where these coils are being fed from, because it may be we can probably guess, just looking at the geometry, that these are contact pads that I'm using to feed these coils, but COMSOL doesn't know that. We need to tell it so. So you'll notice that each of these conductor nodes has a terminal condition underneath it, where we're invited to specify a current and 1 or more boundaries on which that current is coming in. So in this case, for example, I can select conductor 1, which we'll notice is this one here. And then I can assign the terminal to be the input point for a current, which I could type in this box, to this coil. So for example, I might point and click on this boundary here to say, this is like my high voltage boundary, this is where the current is coming in. I then also need an output. So how does the current get out again? So I can right click on here, and you'll notice I have a ground option where I can ground the output boundary. So I can add a ground, just clear the selection by pressing this clear selection button here, because it selected everything by default, and then just click this one here. So this setup is like saying current is coming in here, and I'm applying 1 amp. You can think of that as a test current, if you will. And then a ground boundary here. So that's where the current flows out and goes to the ground. So I would need to repeat this process for each of the other coils. So I would need to tell COMSOL that this is the input for this coil, this is the output, this is the input, and so on for all of the 12 other conductors. So to save you watching me click on a lot of things, I have this version here, which is the same model that you just saw in the same state, except before this talk, I've gone through and selected all these sort of input and output points. So you can see right the way down to conductor 12 here with its input and output. So the next step on the way is the mesh, which is down here. So if I click on the mesh, you can sort of see what this does quite visually. This has filled my geometry with a series of, in this case, tetrahedra. And you can see the triangles, which are the outsides of those tetrahedra, like so. So the finite element numerical method that COMSOL uses is a way of discretizing a problem like this for solving computationally. And the way it does that discretization, well, a sort of simplified picture of that is to think that it's solving on each of these points for the values of the electromagnetic fields and currents. So all of the vertices of these tetrahedra. The idea being that as I make these tetrahedra smaller and smaller, we would approach the sort of correct continuous solution that you would see in real life. Although there is a trade-off to that in that the smaller the tetrahedra, the more unknowns I have and the longer the model will take to solve. So I can just use the default mesh in this case for demonstration purposes. And then finally, we have the study down here. So the study was added earlier via the menu that I went through at the start, which asked us these questions. It has a source initialization and a frequency domain source sweep. So the source initialization essentially computes the current path. So it goes to conductor 1, for example, and then it says, okay, the current's going in there and it's coming out there. So how do I get from that boundary to that boundary? And it will work out all the loops that it needs to do to get there. And then it will do the same for conductor 2 and conductor 3 and so on and so on. So in some sense, this is an initialization step, working out how the current is going to flow in these coils. Then once we've worked that out, we have a frequency domain source sweep. So in this, I can specify a frequency via this box here. So I can just say 200 kilohertz, for example, but you'll notice I could type any frequency I wanted in this box, as long as it fulfills the assumptions of the physics interface, which was that we're working at low frequency, so radiation can be neglected. And then what this will do is it will do a source sweep. So it will apply a current, an AC current of 200 kilohertz frequency and 1 amp peak value, because I specified 1 amp in here, and it will apply it to conductor 1, solve the model. Then it will apply it to conductor 2 and solve the model, conductor 3, and so on and so on. So essentially it will solve 12 times for the 12 conductors. So we can see the field pattern we get, exciting each one to one after the other. So there's some other settings here to do with the solvers and so on, which you don't need to mess with for a sort of initial case. And then the compute button is up here to tell it to solve the model. So computing these models can take a few minutes. So this one takes a few minutes, I think. So once again, I'm going to do the trick of going over to the solved version. So this is the same model. You can see the same contents here. And you can see that when I solved this before delivering this talk, this took 17 minutes to get to this point. Although your timings may vary depending on your computer, obviously, in this case. So once you've solved it, waited the 17 minutes, it gives you these default outputs. So it gives us a plot of the magnetic flux density and some what it called lumped parameters. So the magnetic flux density plot appears here, first of all. If I click on it, you can see this is a very nice plot where I can visualize the magnitude of the magnetic flux density and the direction of the field lines. And you can see this is the case where this particular conductor was excited, which I think was number 12. So you can see that here. I also have these arrows here where I can sort of step through and you'll see the different solutions. So if I step back on this arrow, it'll take a couple of seconds to render the graphics in. And then you'll see the solution with this conductor, I think it is, being excited rather than that one. And you can sort of inspect the 12 different solutions in that way. So you can sort of visualize results like that. And you can visualize lots of other things as well. I mean, I won't go into it in this case, but if you look into these results plots, you can change what you're plotting. So you can plot the currents, you can plot the electric fields, and so on. So complete flexibility in that sense. You can also extract what it calls lumped parameters. So these are numerical outputs for the whole model. So in a case like this, a common thing that people want to look at is the complete inductance matrix between the different coils, the 12 different coils, which is a 12 by 12 matrix in this case. So you'll see there is an inductance AC option here. And if I click on it, it's actually automatically computed for me this inductance matrix. And the way I can tell what these are, by the way, is my conductors were labeled 1 to 12. So this is 1 to 12 along there and 1 to 12 along there. So this is the sort of self-inductance of coil 1, coil 2, coil 3 down the diagonal. And then this is the cross inductance from coil 1 to coil 2 and so on. So you can extract these very quickly and easily for any set of coils that you may have in your model if you set it up in this way. So it's possible to get other numerical outputs from these things as well. I mean, you can see already it's given us by default the impedances. So these are the impedances as seen on the coil inputs for these different coils, real and imaginary parts, at the frequency that we used. You can get other lump parameters as well, such as the voltage that you would need to apply to drive this much current through the coil and that sort of thing. So hopefully that gives you a taster of how these models work. If we can go back to the slides now, please. Yep. So I'll skip. We've only got a couple of minutes left, so I will skip through to the end here. So yeah, so what I showed you there is what we refer to as an AC-DC model. So it's computing the electromagnetic fields at low frequency. So COMSOL Multiphysics is, however, a very broad software suite, which is actually split up into a series of different modules via different areas of physics that you might want to compute. So essentially, if you have a COMSOL distribution, you get a core package, which is on the left of this slide, which gives you all the things like the solvers and the meshing and the geometry and all the basic functionality like that. And then we have a series of add-on products, and I've just flashed up this the list of all our add-on products on this last slide in case any sort of catch your eye. You can see we have different modules tailored to a very wide variety of different areas of physics and even chemistry. So the example I showed you was the AC/DC module for low frequency electromagnetic field modeling. There's also an RF module for working in the RF range. So maybe your PCB is working in the gigahertz range, for example, then the RF module would be the one for you there. There are optical modules for optical effects. And there are even these other modules for heat transfer, fluid flow, chemistry, and so on, as well as interfacing products. So like I said, you can derive your geometry from CAD products. There's a big list of CAD products via these LiveLink modules you can see on the right-hand side that you can use for this. And you can also even get more complicated and do things like optimization algorithms for optimizing your geometry, uncertainty quantification, for trying to work out design tolerances in your geometry, that sort of thing. Or this so-called co-simulation. So you can link it up to either MATLAB or Simulink. And for example, I can use a Simulink block diagram as a control system to feed or control my 2D or 3D COMSOL model in a sort of fully coupled, sort of joined up way. So that gets very powerful and very flexible if you want to go that way. Okay, so that's just about the end of my talk. So if you're at all interested by anything that we've shown here, or if you just have any questions based on this talk, then we will be very happy to answer you. And your one-stop shop for doing that is if you get in touch with us at the contact details on our website at comsol.com/contact, as shown on this slide. Then we can direct you to the relevant person based on your query. So yeah, I hope this talk was been of use and interest to you in giving a taster for what can be done with the with COMSOL Multiphysics. And yeah, please do get in touch if you'd like more information. So yeah, I don't think we have any questions through the chat box. So yeah, thanks for listening, everyone, and enjoy the rest of the show.